So we've got Rick Hess to talk about the Heartbleed vulnerability.
Do you want to use the slides? This one is forward, as long as it's working.
See, it hates me today.
All right. Down arrow, up arrow.
Okay,
Okay.
gotcha.
Thanks.
All right. My name is Rick Hess, and today I'm going to talk about NASA IV&V and our work towards the Heartbleed vulnerability. Um, All right, so just a quick agenda about what I'm going to talk about today. First off, I'm going to briefly mention what OpenSSL is and go into some specific pieces to that. What versions of OpenSSL were affected by the Heartbleed, how NASA can protect against this type of issue. This has been a concern for us here at NASA IV&V. Kind of results we've seen, what's happened since this. We originally give this presentation internally to IV&V. Well, there's been some more activity since, so I'm going to briefly talk about that. Some takeaways that we can all kind of bring back and actually learn a little bit from this experience. And special thanks to the people that were participating, and then we'll get to questions. So let me go ahead and start. So according to Google, OpenSSL was basically an open source implementation of the Secure Sockets Layer, SSL, and Transport Layer Security Protocols. The core library was written in the C programming language. The wrappers are allowing the use of OpenSSL, the OpenSSL library in a variety of computer languages. It's free. And what's shocking about this is it's free, but 2 out of the 3 web servers in the United States use OpenSSL. So it is something that is freeware that a lot of people use and a lot of servers use, obviously. The Heartbleed extension, so OpenSSL Heartbeat was an extension for this particular tool, this OpenSSL. And it provides a way to test and keep alive secure communication links without you having to renegotiate or reconnect every single time. So according to Mark Cox of OpenSSL, Google's security team actually found this Heartbleed vulnerability on April 1st. The defect could be used to reveal up to 64K of the application's memory with every single request. It wasn't something that had to break a firewall. It was functionality that was readily available to people, and it's something that anybody could basically ping and get. So the affected versions would allocate a memory buffer for the message to be returned based upon the length of the requesting message. So that sounds okay, meaning that I would say, I want 4 characters. This is what I expect to hear back. It would give me that back. But I could actually request more than that, even if I said 4 characters. For example, in this image, I could say bird, 4 characters, and it'll give me back bird. But if I say bird and give me 500 characters, it will give me back whatever's on the buffer. So then I could go through that, see what kind of information I could get. I might be able to do multiple heartbeats to be able to just get a big section of data so I can just parse through it. So right before I go any further, I mean, again, this thing was on 2/3 of the servers, they say in the world, definitely in the US, and it's free. So it's one of these things where you think that there should have been some sort of testing done for this. We'll get into this a little bit more later, but it's just a thought to put in there to think, something so secure of a piece of software, you would expect some sort of rigorous testing to be done with it. So from a low level, there's a memcopy function. Again, this was written in C. So basically, the memcopy function would take elements from the variables, put one into another, and it copied the data, and it was sending out this data. So the variable payload was used to store the size. Well, that variable could range. And since 64K was the biggest value that the payload variable could be, that's the limit to how much data you could get back. It actually begins uninitialized and is specified per the user. So the user can determine how many characters that they want to see back. And again, it's a 4-byte array unassigned. So it was introduced. So where did this all begin? Well, the Heartbleed bug was introduced to OpenSSL in December 2011. And it's been out in the wild, actually released on March 2012. It was actually fixed on April 2014. So there's been about 2 years there that people could have installed it on their servers and actually had it running, and no one really knew. So the good news is the previous versions before March 2012 were not vulnerable, and of course the newest branch that's been created is also not vulnerable. But most people would regularly update their software, so until April 2014, you probably had the newest version, or you were trying to use the newest version, and may have had that vulnerability already in it. So a little bit more information about the concerns that we have with the maintenance. After this had happened, one of the things that the OpenSSL Software Foundation president had said was, even if small donations had arrived at the same rate, it would not be enough for the project. They claim that they're nowhere near enough. It is nowhere near enough to properly sustain the manpower levels needed to support such a complex and critical software product. They were literally just creating the software, making it free for people to use, and they actually got their money from doing installs of the software. They weren't selling the software, so they were really not doing integrated testing. There was no funding for that. So they're actually surprised, if anything, that more bugs haven't came out of this. According to the second point, they say, striking out the comments, it says, given the widespread use of OpenSSL over many years, it is an excellent track record, even considering this vulnerability is there. And it took 2 years before somebody had found it. So the question is going to be, why? Why did they not find it? Was it because of it was actually so obscure, or was it because of a lack of effort, or was, is it a combination of both? And when I say lack of effort, I mean, was it just something we assumed to be secure? So at NASA here, we've had a request sent out to determine if the tools actually determine the Heartbleed issue that is here on these servers. Is there some way that we can find this data? So a quick turnaround effort was created between SCOG, which is a code analysis working group that we have here at the facility, which I'm the lead of, and SWAT, which is Software Assurance Tools group. They do a lot with maintaining our software tools here at the facility. So after working with multiple tools on this idea, at least one of these tools that we used to perform code analysis on the OpenSSL build, we used one of the vulnerability builds. We found that at least one of the tools found it out of the box. By this time that we had done this analysis, there was a couple other tools that had claimed that they had found the specific issue or now had checks for the specific issue, but there wasn't anything out of the box. So it's out of the box when it comes to some of these problems. So we did find at least one tool that had it. We actually have a capabilities matrix where we collect a list of tools and we collect a list of checks, and we actually added that defect to our matrix. And so that way we can try to keep track of it. But this actually scares me a little bit more that we were able to find it using a static code analysis tool. Why not do that for this code if you expect that within 2 years on a secure piece of software there would have been some kind of rigorous effort put towards this. Now let me say this too. I mean, we have analysts here that are proficient in code analysis. So, it's a combination of also not only the tools, but also the analysts. Um, that's kind of why, I mean, it's one thing just to get results back from a specific code analysis tool, but it's another one to have an analyst go through and try to determine whether or not there's real defects. So, with all that said, the real question is, since we were able to use static code analysis tools, could there be more defects? Is there something that we should do to try to determine if OpenSSL has more vulnerabilities in it? So with that, I'll actually add one more thing to this. We've got the problem of, there's not enough effort being placed on trying to do testing with open source tools. This is one particular version of an open source tool. And, the question is, we kind of assume these things work and we kind of just put them in because they're heavily used. But how many people actually go through and do testing on that open source software? We're always assuming that somebody else is doing the work. So internally within an IV&V, we do a lot of stuff with code. We do a lot of stuff with software testing. It's also important to think that we need to also look at those open source libraries and not just, particular piece of code that has to do with a spacecraft. A lot of the libraries and stuff also need to be analyzed because if a problem exists there, it could affect the spacecraft code. So it's one of these things where it was kind of an eye opener for me to make sure that we're checking all of our libraries. So what's happened since this is, although we wanted to kind of break out and say that we could at least use one tool to find this defect. A collaboration of different companies, in fact, Linux, Google, Microsoft, IBM, and many others have came together to actually support critical open source projects like this one, called the Core Infrastructure Initiative. So after this had happened, they realized that there needs to be testing for these tools, especially if we're using them. So the website claims that the steering group will work with an advisory board of esteemed open source developers to identify and fund open source projects in need. In other words, you can go to the site, you can donate. They're basically putting together money, millions of dollars to try to do integrated testing. And they came across with the same ideas that we had, which is we really need to do testing with open source software, even if we're getting it from where we think is trusted resources. There's no harm in doing some testing. And in fact, we'll give funding to those open source projects to be able to do their own testing, and we can help with that. So with that, again, the takeaways, this is a fairly quick presentation, but some takeaways that I can take away from this is it's okay to question third-party libraries. It really is. If there's some things out there that we're just integrating into our system, we shouldn't just assume that everything is okay. It may actually warrant us to go back, try to determine if we need to apply some rigor towards doing some testing of these open source software pieces. And again, you just can't assume adequate testing's always been performed. A lot of times they say that they've been adequately tested. I mean, according to the OpenSSL, the way that they tested this is they took the Heartbleed stuff, they implemented it, they had one person look at it, he ran one or two tests against it to make sure that everything looked good, and then they released it. So there was no integrated testing going on, and of course with something so critical that's being used on 2/3 of the servers here in the US, it really is something where more testing should have been done. But again, it's a security piece of software, so everybody else already assumed that it was being integrated and fully tested when it was being done. So with that, I'll just go ahead and say that if you'd like more information about some of the stuff that we've done with the Heartbleed, if you have any questions, you can contact us at SCOG, which is the Static Code Analysis Working Group. or the software assurance tools team here at NASA. And let me see if I've got. And finally, some special thanks that I want to give. Marcus Fisher and Rich Brockway in the back there. I want to thank them for all their hard work. At the same time, I also wanted to thank the SWAT members, Jerry and Chris Williams, for helping me perform this activity in such a short turnaround. I think we had 3 or 4 days worth of work into it, and you know, it was a really big eye-opener for us. So with that, I'll go ahead and open it to any questions.
Yeah. You said that using the open source, probably we should take some prudent steps as asking for little more testing on those open source
Well,
codes.
I would say this: if it's just understanding what kind of assurance you can gather from the testing that they've done. You would like to know that it's been adequately tested. It doesn't mean that we have to absolutely go through and test everything, right? But it's something where we should be asking ourselves, what is it that we need to do to make sure that this software is complete for us to use? And whether or not that's our testing or if that's you know, testing that they're doing on their end to provide assurance to us, that's something that we can figure out. And also, you know, we're in a world where we have limited rigor. So meaning that we only have a certain amount of time to do things, but it's nice. It's just something that we should put into our list of items that we should think about and kind of prioritize that. So.
Actually, I was trying to point out about one particular thing about the open source. Most of the embedded world will use some kind of a cross compiler to actually generate the code for your target processor.
Yes.
And most of the time, these cross compilers are open source codes, right?
Yeah.
So what does that mean is that most of the time, do you mean to say that are these guys using suspect software, or they should be testing more, or IV&V should be putting more emphasis on that, the basic process, you know, that they're generating the main executable out of
Yeah.
the software that you're doubting now. So.
I totally agree with that. I think that's another piece to this to actually look at. And it doesn't have to be necessarily open source software. I mean, it could be paid software as well. We have some of the same concerns. So that's important to note. Yeah.
And the UNO compiler.
Yes. Oh, yeah.
I mean, that's at the heart.
Well, yeah. Yeah. So. All right. Sure.
I suspect the reason most people were happy using it was everyone used it and they knew it did what it was supposed to do. But the challenge, of course, was to test it so that it wouldn't do what it wasn't supposed to do when it was maliciously used. So
Yes.
can you say a little bit more about how you folks test for that kind of vulnerability?
Well, actually, let me just start off by saying I don't really want to go into the details of the tools that we used and the kind of, we've been kind of shunned away from trying to talk about our approaches here, but more along the lines of the issues that we've had here with the Heartbleed stuff. But I will say that it was literally something where we had a request from NASA headquarters. They wanted to know what we could do to try to calm down this problem. Because at that time, it was a big issue. So this was actually a little bit different than our normal efforts because it was a quick turnaround effort that we had. So we were trying to get feedback as soon as possible. So we ran a bunch of tools. We picked out a earlier version of the software that had the vulnerability in it. Made sure that we adequately knew what the vulnerability was and also how to, you know, what the problem was. And then we ran it against a bunch of tools. We also took some compilers that had, or some static code analysis tools that had the check already in it. We had some that had, when I say that, I mean there's something that it was doing to already find it. There's some of them that they added the Heartbleed stuff after the fact, right? If I'm a code analysis tool developer, I'm going to say, hey, you add this stuff in, I can find it for you, right? So we took some of that. We've seen how efficient it was. Some of them just were looking for a particular functioning. Well, that doesn't help us much, you know. Other ones did go a little bit more in depth, but it was kind of scary for us because we didn't know what kind of results we were going to find. So it was nice for us to be able to come back and say, yes, we can find it. There's at least one tool that we have that does this. So now we can take that information, go back and say, yeah, we can find it if it's available. And also it's the knowledge of the analyst to be able to, you know, detect that. I mean, so the tool is half the battle. The other half is actually the analyst being able to recognize that that is a legitimate problem and not just a false positive. So our process was literally just to try to take the tools that we had, try to run the code that was vulnerable against them, try to see what kind of results we got, take the updates that some of these code analysis tool developers had for the vulnerabilities, seeing how easily they worked, and try to make our judgment from that. So,
Thank you.
thank you.
Probably in a unique position here to actually comment on this from the other side.
Okay.
I'm the RTIMS project lead. I'm on the GCC steering committee, and I'm on the Network Time Foundation board.
Okay.
So I could probably spend the rest of the day telling you how this works from the other side, but I'm just going to say that we have about 15 years experience with NASA and the European Space Agency, and we don't have access to the tools except through the free Coverity Scan program. We generally don't get feedback from anybody's IV&V programs, and we have limited resources. Even when and I know RTIMS cares, we have limited resources to actually plow through the code sonar or the Coverity results are good, but we have limited resources to even plow through the results. So,
wow.
I'm just being blunt. I mean,
no,
that's one of the reasons I'm here is to try to see things from the other side of the coin for a change.
Well, no, that's fine. I actually, you know, it's one of those things where, first of all, question is there something that we can do with our analysts and our tools? I mean, we have licenses for all these different tools, and we have analysts to be able to run them. So if there's something that we can do to work with you guys to be able to help try to provide assurance, that might be something to do.
That's kind of what I've been asking, because I've been on a personal quest for like a number of years now. But
well,
it's always a matter of who you meet.
Oh, no, that's
and
fine.
The right people at the right time.
I definitely would like to talk to you offline about this,
Yeah.
and I know a couple other guys would too. But all right, thanks.
Actually are out of time.
All right.
Yeah, we're going to catch up-ish right now, so thank you very much.
All right, thank you.